So in this question, we are investigating the reaction between two different solutions of sodium carbonate, solution K and solution L with hydrochloric acid. So first we rinse with water to remove any impurity. Then we rinse with hydrochloric acid to remove the water. Then what we did, a burette was filled with a hydrochloric acid, and then we opened some of the hydrochloric acid was run out of the burette. What is the reason for doing this step? To remove any trapped air present or remove the air from the burette. That's why we did this. Then we took a measuring cylinder, and using a measuring cylinder, we took 25 cm cube of solution K and we transferred that into a conical flask. So solution K was transferred into a conical flask, and then we add 5 drops of methyl orange and then 5 drops of thymopethylene indicator were added into a conical flask. So two indicators are added, not one indicator. That's why even though because this was sodium carbonate, Na2CO3 or alkaline solution. So in alkaline conditions or in alkaline solution, what is the color of the... So if you have alkaline conditions, what is the color of the methyl orange? Methyl orange in this is the methyl orange. In alkaline, it is yellow, and in acidic, it is pink. But because there are in this experiment two different indicators are used, so it might have a different color, or there might be a color mixing as well. So 5 drops of methyl orange and 5 drops of the thymopethylene indicator were added. The conical flask was placed in a white tile so that we can observe the color change easily. Hydrochloric acid was added from a burette to the conical flask while the flask swelled. Mainly conical flask, we use it so that we can swell the mixture easily until solution turned yellow. This is the first color change. Then more hydrochloric acid was added into a conical flask until the solution changed the color again, and that is the second color change. So solution, this is showing a color change twice because two different indicators are used. So they can change a color different pH. Now the first part, you can use a screen annotation, use a burette tree diagram to complete the table. Use the screen annotation to complete this table. The first burette reading at the first color change. Now this you will fill it afterwards. First you have to fill this part, initial burette reading, final burette reading, and then reading at the first color change. How we identify that? So initial burette, this is the initial burette reading. I will fill this for you. I will fill, just a minute. I'll fill this for you. And so you will have an idea. If you see, this is the burette reading at the first color change, then the final burette reading at the second color change, then the initial burette reading, that is cm cube, then a volume of a hydrochloric acid added to the first color chain, and volume of hydrochloric acid added to the second color chain for the second. So initial burette reading. What is this initial burette reading? This is initial burette reading. We have to fill this row. So how much is the initial burette reading? This is 1, 1.1, 2, 3, 1.5 is there. And we read the lower or the bottom of the meniscus, so it is 1.6. And the unit is already given centimeter cube, so it will be 1.6 cm cube. Is it clear, this one?
Yes.
Then burette reading at the first color change. So burette reading at the first color change means this value. So how much is this? We always use the bottom of the meniscus, so it looks exactly 12. But don't write 12, write 12.0 because the smallest value which it can record is 0.1 cm cube. So don't write only 12, write 12.0. So that's equal to 12.0. Then the burette reading at the second color change. So burette reading at the second color change, this one, how much is this? This is 22, 20.1, 2, 3, and 4. So that's equal to 22.4. So we write that as 22.4 cm3. Now, volume of hydrochloric acid for the first color change. So this was originally, and this is how much the difference is there between these two volumes. Like this was 1.6 centimeter cube, or like it was filled originally 1.6, and when there is a color change, the volume or the burette reading was 12.012. So how much difference is there? So the difference, how much liquid is removed. So originally it was 1.6 was already there. Like 1.6 is already removed before the experiment. And then when we remove further for a first color change, it shows a color change at 12. So how much it has removed? That is right, 10.4. And for the second color change, this value is how much? This value is 22.4. So for the second color change, when we start, it was originally. So how much the color change is there for for the second color change? The total volume which is removed from the initial total volume of hydrochloric acid, because we need the total volume of a hydrochloric acid added. So what is the total volume of a hydrochloric acid added? So 20.8, because when you subtract, like originally it was 1.6 and now 22.4. So how much it is? That is 20.8. So these are the color changes, like the volumes which we add from the burette so that the color change happen or occur. So first color change happened when it changes from 1.6 to 12. The second color change, the total volume from 1.6 to 22.4. That's why it was 20.8. Yeah, they asked for a second color change, but if you read the total volume, the total volume is from the beginning. Total volume for the second color change, we always take from the beginning. Like when we did, we continue from the same burette, we added the acid. The first color change happened at 12. The second color change happened at 22.4. But how much the volume has removed from originally? So that's why we always take from the initial value or initial reading. Is it clear, this one?
Yes.
The next one, experiment 2. A conical flask was emptied and rinsed. Now you have to complete, the conical flask is emptied and rinsed with distilled water. The experiment 1 was repeated using solution L instead of K. Now, because first we did solution K, now we are doing with L. Use the burette diagrams to complete the table for experiment 2. The burette, now use screen annotation to complete these. Initial burette reading is 4.1, that's right. The burette reading at the first color change is 19.7. The final burette reading is 35.1, 2, and 3. Volume of hydrochloric acid added to the first color change. How much hydrochloric acid was added to the first color change? Like in this one, changes from here to here. That's right, 15.6. And how much hydrochloric acid is added for the second color change? Total volume of hydrochloric acid for the second color change. Yeah, that's right. So it is 31.2. So 31.2. So overall, if you see for solution K, for a complete color change, we need 20.8 hydrochloric acid. And for solution L, we need 31.2. Like if I draw this figure, like representing them to identify the concentrations of the solutions. So when we did the experiment, we took 25 cm cube of solution K and we took 25 cm cube of solution L. And we add the two indicators, the methyl orange and thymopethylene. And from the burette, we are adding HCl. The solution L and the equal amount of solution L and K. Solution K was 25 cm cube. Solution L is also 25 cm cube. But from the burette, the hydrochloric acid, the same hydrochloric acid is there. Solution L, K and L are unknown, like we don't know their concentration. So for this, for a complete color change, we need 20.8 cm cube of HCl. Here we need 31.2 cm cube of HCl for a complete color change or complete reaction with L. Can you identify which solution is more concentrated? Which solution having more reactant particles? Is it K or L? Which solution? You can use your mic or a chat to state the answer. Which solution appear to have high concentration of particles? Is it K or is it L? We know the same type of hydrochloric acid is used in both experiment. Like experiment 1 and experiment 2, we use the same type of hydrochloric acid. But the only difference, the solution K and L are different. So the correct answer is L. L is more concentrated because L need more amount of hydrochloric acid for a complete reaction as compared to K. Or we can also say L has more particles, that's why it need more hydrochloric acid as compared to K. Because equal amount 25 cm cube, 25 cm cube, but the hydrochloric acid which we need to react, we need only 20.8 cm cube of hydrochloric acid for experiment 1. But for experiment 2, we need 31.2. Like we need too much hydrochloric acid to react with L. So it means that L has more particles or L is more concentrated. Then we have to state the color change observed at the end point when dilute hydrochloric acid is added to methyl orange in alkaline solution. So what will be the color change? So observe at the when dilute hydrochloric acid is added to there, that's good. Initially it will be yellow, pink acceptable, orange acceptable. For experiment 1, compare the volume of hydrochloric acid needed for first color change with hydrochloric acid for the second color change. So we want to compare the volume needed for a color change. For experiment 1, they asked. For a first color change, this was, I guess, 10.4 was there, and this one is 20.8. What is the comparison? How I like what ratio they have for the first color change and for the second color change? What is the ratio between them? First color change, we need 10.4. Second color change, 20.8. Can you form a ratio or relation?
1:2.
1:2. You can see it's like for the second color change, the volume needed is twice as compared to the first color change. So answer here, because like one is 10.4, another is 20.8, it's like double. Or you can also say the volume for the color change is double or greater or twice or 1:2 is a ratio. The volume for the second color change is twice compared to the first color change. And how we identify it's twice? Because you just compare the volume like 10.4 and 20.8. So it appears it is twice. Compare the concentration of solution K used in experiment 1 to concentration of solution L in experiment 2. It's of 3 marks. First thing, which solution is more concentrated? Just now I explained to you, like we took equal amount of K and L, and for the hydrochloric acid, here we need 20.8, here we need 31.2 HCl. So which solution is more concentrated, K or L? L is more concentrated than K. Then you can also compare their ratio. What is the ratio between 20.8? Like here we need 20.8 hydrochloric acid and here we need 31.2. So when I take the ratio, it's like 1:1.5 between them. So how you score 3 marks? Number 1, you will mention L is more concentrated than K. That is 1 mark. And how you conclude that? Because greater amount of HCl required to react completely with L compared to K. And how you score the 3rd mark? You can just compare the volume ratio. You take a volume ratio, how you can do? You will divide by the same number. Like example, if I divide both of them by 20.8, like the smallest number in the ratio 20.8, so I'll get the simplest ratio. This will be 1 and 31.2 divided by 20.8. That will give 1.5. So 1:3, simplest ratio is 1:3 between them. So ratio of the volume of acid use 1:1.5, not 3, 1:1. Or 2:3, 1:1.5. Is it clear, this one?
Yes, clear.
The next one, deduce the volume of a hydrochloric acid for the second color change when the experiment 2 was repeated with 50 cm³ L. Look, first, when we did this experiment, we took 25 cm³ of L. And how much hydrochloric acid was needed? Hydrochloric acid needed was 31.2 cm³ for 25 cm³ of L. They're saying if we double the volume of L, instead of 25, now it's 50 cm³ of L. How much HCl is needed? So if 25 need 31.2, 50, double of it, how much it need? So it will be twice of it, like example, double, so it will be 61.4 cm³. Because if 25 need 31.2, so 50, which is a double volume, it need double amount of 62.4, not 61, 62.4 cm³ of HCl is needed. Because if we double the amount of L, we need double amount of hydrochloric acid. But what is the problem with this if we use 50 cm³ of L? Because if we from a burette we are adding hydrochloric acid, and burette can maximum hold 50 cm³. That's a maximum which burette can hold. So if I want to add 62.4 cm³ of hydrochloric acid from burette, what I have to do? I have to refill the burette, because maximum volume which we can use from the burette is 50. If we need more than 50, then the burette must be refilled. So deduce the volume here. This will be, yeah, how you get 2 marks for this? 1 mark, you will predict the volume, like you said, 62.4 cm³, that is 1 mark. And what is the second mark? Because the volume double. So double volume of L, you need double volume of HCl. And why using a 50 cm cube L cause a problem? The problem is we have to refill the burette. Then state advantage of using a pipette instead of a measuring cylinder. How it is a problem during the experiment? Because what you have to repeat the same procedure. How refilling a burette is a problem? Because what might happen when you refill, there will be again air will enter. Then you have to open the tap and remove the air again. You have to do the whole procedure again. That's why it's a problem. State an advantage of using a pipette instead of a measuring cylinder. What's the advantage of pipette? It's more accurate. That's
More
right.
accurate.
Explain why conical flask was swelled as dilute hydrochloric acid was added from the burette. Why we always swell? What is the reason for that?
To mix.
Mix the solutions so solutions can mix easily. Then at the start of experiment 1, the burette was rinsed. It's a similar question. At the start of experiment 1, the burette was rinsed with water. And then it is rinsed with hydrochloric acid. At the start of experiment 2, conical flask was rinsed with water but not with solution L. Explain why conical flask was rinsed with water. What is the reason why we rinse with water?
To remove impurities.
To remove impurities, to clean, to remove any residue from experiment 1. Because we've rinsed. And why conical flask was not rinsed with solution L in experiment 2? Like both time we rinse with water. So what might be a reason for that? No, not about the reaction, because in the question they mentioned, like when we did the first experiment with K, like experiment we did first, we did experiment with K. When we finished the first experiment, we rinsed the conical flask with water. Why we remove the rinse? Why we rinse the conical flask with water? That is to remove solution K. That is the main reason, or any impurity, because this was done in experiment 1, it was filled with K. Then in experiment 2, we have to fill with L. But before fill it with L, we rinse with water. Why we rinse with water? To remove K. Any impurities or any substance K left in the flask. Then what we did, when we did this experiment, like why the conical flask was not rinsed with solution L. After rinsing with water, why we did not rinse with L? Because what might happen, like in the conical flask, if we rinse with L, then this conical flask might have some L inside. And when we add 25 cm cube of L for the experiment, so the total volume will not be 25, the total volume will be more than 25. So that's why the conical flask is not rinsed with L. Otherwise, if we rinse, well, like we just rinse with water, we did not rinse with L. Because if we rinse with L, some of L will be there initially, and then we add 25 cm cube. So the total volume of a solution L in the conical flask will be more than 25. It won't be equal to 25. So here the reason is, so the total volume of L in conical flask does not change.